Episode 8. The Thermocline, the ocean's invisible wall. The ocean looks like one thing from above, a flat surface, a single color. But underwater the ocean is not a space, it's a stack. And inside that stack, sound doesn't travel like a straight arrow. It curves, it bends, it hides. Sometimes the ocean behaves less like water and more like a lens. That's the strange part. Sound can travel astonishing distances in seawater, far beyond what light can do, and yet submarines can still disappear in plain acoustic sight. So how can sound travel so far, while a vessel the size of a building can vanish? Today, we solve that paradox, not with magic, with physics, and with one invisible layer that turns the sea into a map of hidden corridors and blind spots. Here's the model card for this episode. A submarine doesn't only hide by being quiet. It also hides by choosing the right depth, because the ocean bends sound in predictable ways. To understand that, we need three facts. Three pieces that snap together like a lock. First, the speed of sound in seawater is fast, roughly 1,500 meters per second, but it's not constant. It changes with three main variables: temperature, salinity, and pressure. Temperature tends to make sound faster. Warmer water, molecules move more easily, sound moves faster. Colder water, slower. Salinity also nudges it upward. More dissolved salts can increase sound speed slightly. Pressure increases with depth, and that also increases sound speed. So you can think of it like this. Near the surface, water is often warmer, faster sound. Go down a bit, temperature drops. Sound slows. Go deeper still, pressure becomes dominant, sound speeds up again. That means sound speed in the ocean often forms a curve with depth, not a straight line. And whenever a medium changes speed with depth, waves bend. Second, when sound moves through layers where its speed changes, it refracts, it curves. You already know this behavior from light. A straw in a glass looks bent. That's refraction. A wave changing direction because its speed changes in a new medium. Sound does the same thing in the ocean, just slower to visualize and harder to see with human senses. If sound enters a layer where it travels slower, it bends toward that slower region. If it enters a faster region, it bends away. So the ocean is constantly steering sound rays up or down depending on the speed profile. And now we're ready for the third piece. The one that makes submarines smile. The ocean often contains a sharp transition layer where temperature changes quickly with depth. This is the famous invisible wall, the thermocline. A thermocline is a layer where ocean temperature changes fast with depth, bending sound like a lens. And here's the practical punchline. If you sit below it, surface sonar can miss you. That's not poetry, that's geometry. In many regions, the surface layer is warmed by the sun and mixed by wind. Below that, temperature drops rapidly over a relatively short depth range. That rapid drop creates a strong gradient in sound speed, and that gradient can bend sound downward or create an acoustic shadow, a region where certain sound paths simply don't go. This is where the ocean stops being one environment and becomes multiple. Let's make it intuitive. Imagine a sonar pulse sent from near the surface. It starts traveling outward, but as it goes, it hits a layer where sound is slower. The ray bends toward that slower region. Depending on the exact profile, it can curve downward, then keep curving, like a skateboard on a half-pipe. That curvature can leave a pocket below the thermocline with much weaker energy from the surface sonar. That pocket is a shadow zone. Not perfect invisibility. Not immunity, but a real, measurable reduction in detection probability. And submarines don't need perfection. They need odds. They need distance. They need uncertainty. Now, here's the important twist. The thermocline doesn't block sound like a wall blocks light. It bends sound like a lens bends light. So detection becomes a game of paths. If the sonar and the submarine end up on a path that connects through the ocean's bending, detection is possible. If the ocean's profile steers the sound away, detection becomes much harder. That's why depth matters so much. A submarine can be quiet, but if it sits in the wrong layer, it may be exposed. And the reverse is also true. Even if something isn't perfectly quiet, the ocean can still make it difficult to hear. So what does this mean in practice? It means the ocean is full of acoustic terrain. There is high ground and low ground, but in sound. There are corridors where sound travels farther. There are valleys where sound fades. There are traps where sound bends away from you. And this terrain changes with time of day, season, weather, currents, and location. A storm passes through, the surface mixes, a layer weakens, a corridor shifts. One day a thermocline is strong and clean, another day it's blurred and broken. The ocean is not a static map, it's a living one. Now, if the thermocline creates shadows, does it also create highways? Yes, sometimes the same physics that hides you can also let you hear farther. Refraction can create ducts, layers that guide sound horizontally, keeping it from escaping upward or downward too quickly. It's the same basic idea as an optical fiber, a wave trapped by continual bending back toward a region. In the ocean, these are acoustic ducts. If you're in the right duct, you can detect sounds from far away. If you're outside it, the same sound might never reach you strongly. This is why sonar performance is not just about how powerful the sonar is. It's about environment, geometry, and placement. At this point, the story can sound almost unfair, like the ocean is helping the submarine cheat. But here's the counterexample, because reality always fights back. The thermocline is not a universal cloak. Sometimes it does the opposite. Counterexample 1, surface noise. Near the surface, you have wind, waves, rain, ship traffic, biological noise. The ocean can be loud, and that noise can mask signals. But it can also force sensors and submarines to change depth, change speed, change behavior. If you're hiding below a thermocline but you must come shallow for communication or navigation constraints, you can lose your advantage. The layer helps you only if you can stay where it helps. Counterexample 2, deep sound channels. In many oceans, there exists a depth where sound speed is minimal, creating a channel that can carry sound very far. If you're near that channel, intentionally or accidentally, sound can propagate across huge distances. That can be good for detection and bad for hiding. The ocean doesn't choose sides, it just follows the math. Counterexample 3, the wrong thermocline. Not every thermocline creates a helpful shadow zone relative to your opponent's sensor depth and geometry. If an active sonar source is deployed deeper, below the layer, the bending may bring energy right into your region. Or if a sensor array is at a different depth, it may sit on a path that cuts through the shadow. So the thermocline is not a force field, it's a shape, and shapes can be outflanked. That's why real underwater operations rely on measurement, not assumptions. Environmental models, temperature and salinity profiles, ways to map how the ocean is layered today, not how it usually is. Because a few degrees, a few meters, a few hours can change everything. Now let's make this useful. If you remember only 5 ideas from this episode, remember these. 1. Sound speed changes with temperature, salinity, and pressure. That creates bending. 2. The thermocline is a rapid temperature change layer that can steer sound paths. It creates shadows and corridors. 3. Hiding is probabilistic. You're not invisible, you're harder to detect. 4. Depth is strategy. A few tens of meters can change whether a sonar path connects or misses. 5. The ocean is dynamic. Layers shift with time, weather, and location. Yesterday's safe depth can be today's mistake. And now we return to the opening paradox. How can sound travel far while submarines vanish? Because the ocean is not a uniform medium, it's a layered instrument. Sound is the note, the sea is the filter, and submarines survive by learning to play that filter, not by breaking physics, but by living inside it. In the next episode, we'll go one level deeper into the logic of detection. Not just how sound travels, but how you decide whether a faint, messy pattern is a real target or just ocean. Because the hardest part of sonar isn't sending sound, it's deciding what the sound means. Silent oceans aren't silent. They're complicated, and that complexity is where hiding begins.